Hello everybody, I welcome you all to NCAS Geology class. In my last class, I have discussed about the three-dimensional lattices, Bravais 14 Bravais lattices, and two-dimensional arrangement of atoms. And now I will discuss about the 32 point groups and the space lattices. So let us start the point group and space groups. A point group represents symmetry operations involving rotation, reflection and inversion, whereas space groups involves, in addition these three, it involves crew axis, it involves glide planes, it involves the two-fold, three-fold, four-fold bar axis. So let us discuss what is point group and what is space group. Rotation axis involved axis of two-fold, three-fold, four-fold, six-fold axis, and the points on the axis remain here. The points on the axis remain fixed. These are the axis of rotation. Reflections involve mirror planes, where the points on the mirror plane are fixed. In case of inversion, it involves a center of symmetry. So the point group speaks about the external symmetry, that is the shape of crystals or shape of symmetry of the crystal, and it does not involve any kind of translation. In these three types, rotation, reflection and inversion, it produces 32 point groups or 32 crystal classes. Bravais lattices describe the periodic arrangement of points in space using translation. There are 14 types of such lattices possible, that includes primitive, body-centered lattices, face-centered and end-centered lattices. Thus, Bravais lattices show internal translation symmetry. These lattices conform to the symmetry of 7 crystal systems, or we can say 6 crystal systems. The point group must be compatible with the symmetry of the Bravais lattice. That means not every point group can exist with every lattice. A lattice has its own symmetry. The point group of a crystal cannot have symmetry elements that the lattice itself does not support. For example, a cubic lattice contains two-fold, four-fold, three-fold and six-fold rotations, and a monoclinic lattice has two-fold rotation along with mirror. So cubic point group cannot be assigned to monoclinic lattice. Thus each crystal system has its specific lattices and it allows its own point groups. Point groups are possible based upon symmetries involved with rotation, reflection and inversion. Bravais lattices, they involve translation. So there are 14 types of Bravais lattices which include primitive, body centered, face centered and end centered. If we join them with the crystal systems, we can get the point groups. Let us see what are the point groups possible if we take into account cubic crystal system where 3 axes are equal and mutually perpendicular. We can have 5 classes of symmetry. What are these classes? 4 by m, 3 bar, 2 by m, that is the hexatetrahedral class. 4 bar 3m, tetrahexahedral class. 432, gyroidal class. 2 by m 3 bar, diploidal class. 2-3, it is tetratoidal class. These are the 5 classes that are possible in case of cubic lattice. Then in tetragonal crystal systems, we have the primitive lattices, we have the body centered lattices. And there are 7 point groups or 7 classes possible with tetragonal symmetry. These are 4 by m, 2 by m, 2 by m, ditetragonal dipyramidal class, then 422, 4 mm, 4 bar 2m, 4 by m, 4 bar. These are 7 classes, and this represents the normal class or holohedral class. Here in case of cubic system, this represents the holohedral class, and other classes are lower classes having lower symmetry. Similarly, in case of hexagonal system, we have the primitive type, and we have the trigonal rhomboidal class, primitive. So in case of hexagonal, pure hexagonal, it has primitive 7 types, 6 by m, 2 by m, 2 by m, which is usually beryl type, or dihexagonal dipyramidal class, along with other lower classes 622, 6 mm, 6 bar m2, 6 by m, 6 bar. So these are 7 classes possible, and with trigonal symmetry 3 bar 2 by m, 3 2, 3 bar 3m. These are the 5 classes possible. So in hexagonal system there are 12 classes possible. In orthorhombic system we have 4 types: primitive, body centered, face centered and end centered. These are the types possible, and the classes are 2 by m, 2 by m, 2 by m, which is the normal class, then 2 2 2, mm2. These are the 3 classes possible in orthorhombic symmetry. In the monoclinic symmetry we have the primitive type and end center type. The classes are 2 by m, 2 m. These are the 3 types, and in case of trigonal system we have the primitive 1 and 1 bar. These are the 2 classes. So in this manner we have 6 crystal systems, or we can say there are 7 crystal systems. Hexagonal can be divided into hexagonal division and trigonal division. So there are 6 crystal systems in which we are having total 32 point groups or 32 classes of symmetry. When 14 Bravais lattices are combined with 32 point groups, and the symmetry involved with space symmetry operators involving rotation, that is 20 types of screw axis, 20 types including screw axis, and symmetry operators involving reflection, 6 types including glide planes. They resulted 232 space groups which account for the total symmetry of all crystals found in nature. So there are 32 point groups. They are grouped into 7 crystal systems, and each system contains some of the 14 Bravais lattices, and when combined with symmetry operators 20 types involving rotation, 6 types involving reflection along with glide, there can be possible 232 space groups. So we have 32 point groups, 232 space groups. These are in 3 dimension. If you take into 2 dimension, there are 10 point groups, 5 nets, 5 lattice types, total 17 plane lattices possible. So this is all about the plane point groups and the space lattices, space groups, and next we will discuss about the coordination number, and packing fractions, and how a body centered, face centered, end centered lattices contribute the lattice points that I will discuss. So let me start. What is coordination number? Then it will be followed by the packing index. So coordination number, it is the number of atoms with which one atom is in contact. Here the nearest atoms are considered. If this is silicon, it is found to be in contact with 4 oxygen atoms, SiO4 tetrahedron. So we can say silicon is in contact with 4 oxygen. So the coordination number of silicon will be 4. So how many, one atom is surrounded by how many atoms? That speaks about the coordination number. So in case of simple cubic unit cell, the coordination number of the corner atoms of a simple cubic unit cell are discussed here. Around each corner of the atom, there are 4 atoms at a distance. This one, here it is, here it is, here it is, and here it is, here it is. So this one, this one, this one, this one, on the top there will be another. So this atom is in contact or nearer to these atoms at the 6 ends. 4 in the horizontal plane, one on the top, the other at the bottom, at a distance away in 4 directions, and one above and one below. So, there are, we can say, 6 atoms at a distance away from one corner atom. So, the coordination number of this atom will be 6. So, in simple cubic shell, coordination number is 6, particularly with respect to the corner atoms. If it is body centered cubic, at the center of the body there is another atom. In that case, the centrally placed atom is at the body center. It is the body center atom which is equidistant from 8 nearby corners. This one, 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 this one. So, this will be at the center. It will be equidistant from corners, So, for body centered cubic atom, the coordination number will be 8. Similarly, for face centered cubic, it is on the center of the upper face, say, its coordination number will be like this. Around it, if this is the atom, around it we have the 4 corners in the horizontal plane. Nearer to the upper, these 4 atoms nearer to the upper center atom, upper face center atom. Simultaneously, another 4 atoms on the next unit cell, because above it is another unit cell. So, these are the 4 atoms, and this is another unit cell. This central atom is in touch with another 4 atoms on next unit cell, horizontal plane on the top, and another 4 atoms just in the lower cell. So, this central atom is in close proximity with total 12 atoms. So, this is the face. Above is another, below there is so these are the points, in the, if we say this is the horizontal face, we have these 4 corners, we have here, it is another plane here, face 3, 4. So, they are close to this, another above, just above it. Then it's 4 face ends, face centers. These are the face centers. So, we have total, this is close to these corners plus the face, the atoms present on the center of the faces of upper unit cell and lower unit cell. These faces are occurring at the center of vertical faces. So, in this manner, it will have 4 in the plane itself, 4 above and 4 below. In this manner, there will be 12 atoms bordering a face centered atom. Thus, this face centered cubic has 12 atoms surrounding it, so that's why coordination number is 12. In case of BCC, it is 8. In case of simple cubic, it is 6. In BCC, it is 8. In face centered cubic, coordination number is 12. If it is hexagonal closed packing, so this shows arrangement 12. 12 here, 4 here, 4 here, 4 here. So these account for 12 atoms in the faces. Now we discuss about the hexagonal closed packing. Here the coordination number is also again 12. Its coordination number is to be found out. It is in touch with 6 corner atoms. 6 corners. These are the 6 corners. At the center there is atom. Huh? So then it comes in contact with 3 nearer atoms placed within the cell. Here these are the cells. 6. So they will be in contact with 3. On the top there will be 3. So in this manner the central atom will be in contact with 6 horizontal atoms, 3 upper atoms and 3 lower atoms, and in this manner there will be 12 atoms in contact with this face centered hexagonal cubic. So it will have 12 coordination number. Hexagonal closed packing, it will have coordination number 12. And there is another way how we determine the coordination number, that is on the basis of the ionic radii. For example, in Si4 tetrahedron, the silicon oxygen ratio, radius ratio, if you take into account, on the basis of this ratio we determine what can be the coordination number, because it is ultimately controlled by the atomic size. If the atoms will be bigger in size, then in this space a small atom can be accommodated, which can be in contact with these 4 atoms. This happens in case of this Si4 tetrahedron. So let us know these values through which the coordination number can be decided. Here the coordination number for silicon will be 4. So let us discuss these ratios, radius of anion by radius of cation. Based upon these radius ratios, we have the coordination number 3, 4, 6, 8, 12, like this. How this coordination number is found out? Based upon the value of radius ratio of anions and cations. If this radius ratio between the cation and that of the anion, radius of cation by radius of anion, if it is equal to or less than 0.155, then the coordination number will be 2. If it is lying in values between 0.155 to 0.225, then coordination number will be 3. If it is between 0.225 to 0.414, coordination number will be 4. As we see in case of silicon oxygen tetrahedral structure, then from 0.414 to 0.732, it will be 6-fold coordination. If it is from 0.73 to 1, it is 8-fold coordination. If it is more than 1, it will be 12-fold coordination. So, based upon this radius ratio, we have the coordination number. Based upon this atomic packing, as we have discussed in body centered, face centered, end centered, and in simple cubic, what is the coordination number? So, in this manner, the atoms are found to be arranged. One atom is surrounded by other atoms, and based upon the radius ratio, the coordination number is being decided. Based upon the size of the atoms, the coordination number is being decided. So, let us now discuss on these packing fraction. What is packing fraction? Let us discuss how the atoms are being packed. What is the contribution of a simple cubic unit cell? What is the contribution of the body centered cubic cell? So, how the atom, which packing is very strong packing, which packing is loose packing, let us discuss. So, what is the packing fraction? So, in case of simple cubic, each kernel contributes 1/8 of the atom. So, total contribution of the cube will be 1 atom, which is the packing fraction. So, how? So, let us say this atom. This atom is in contact with this cube, this cube, this cube, and this cube. So, this atom horizontally it is in contact with 4 unit cells, 4 cubic unit cells. Above it, there will be similarly 4 cubic cells. So, this kernel is in contact with 4 lower unit cells and 8 upper unit cells. So, this atom is in contact with 8 unit cells. So, if you take into account all the, so the contribution of this atom will be shared by 8 unit cells. So, contribution of each kernel is 1/8 of an atom. And if you take into account the entire 8 kernels, so its contribution will be 1/8 into 8, that will be 1 atom. So, in case of simple cubic unit cell, the contribution of the atom per unit cell is 1 atom, that is the packing fraction for cubic unit cell. If you take any face of this cube, the atoms at the corners are in touch with this atom. So, let us say this is the atom. This is the atom at the face. It is in touch with this this, this and this. So these are, this is 2R, these are. These are is the equal to cubic edge, this edge, this is the edge. So we want to find out this one. So 2R is equal to edge, this is 2R. So now the packing fraction at the face is the number of atoms cross into the volume of one atom by total volume of the cube. This will give rise to the packing fraction. So number of atoms per unit cell, volume of one atom, then divided by total volume of the cube. Suppose in this cube this atom occupy this much volume. So this much volume divided by the total volume of the cube, that will give the packing fraction. So number of atoms per unit cell into volume of one atom divided by total volume of the cube, that gives the packing fraction. So in case of this, in case of cubic, in case of here number of atom is 1. So volume of one atom divided by the total volume of the cube, that will give the cubic, that will give that gives the packing fraction here in case of simple cube. But in case of this face centered cube, what happens? So in case of simple cube, how the packing fraction is found out? Number of atoms is 1, its volume is 4 by 3 pi r cube, and its sides are 2r. So 2r cube, that is the volume of the cube. So if you calculate, it becomes pi by 6, and if we calculate it in terms of percentage, it becomes 52.4%. So packing fraction is 52.4% and rest is free space. This occupies the 52.4% and rest is the free space. So packing, this is the packing fraction when you talk about one atom in case of a cube. This is in case of a simple cube. Now let us discuss how it happens in case of body centered, in case of face centered, or in case of face centered cubic. Face centered cube FCC. Here the atoms are at the center of each face. If we consider any face, we have the central atom to be in touch with the corner atoms. So this is the manner in which the atoms are in touch. So 2R, this will be R, this will be R. So total length will be 4R. If ABC becomes one triangle, if A, B, C becomes one triangle on the face with AC at the face diagonal, having 3 atoms in contact, and the center atom has a radius 2R, side atoms provide radius r plus r, that is 2r. So total length becomes 4r. So this is 4r. Then the side A, this is A. So a square plus a square is equal to 4r so whole square. So 4r into 4r is equal to a square plus a square, that is 2a square. So A becomes 2 root 2r. So packing fraction will be Z into volume of the atom by volume of Q. So in FCC, face centered Q, total number of atoms per unit cell will be 4. How? As I have already discussed, this is 1, this is 1. The all faces, they have their contribution of 3 atoms, plus all these center, all these primitive points, they have 1 atom. So there will be 4 atoms per unit cell when you talk about face centered atomic arrangement. So in FCC there are 4 atoms, Z is 4. Number of atoms per unit cell is 4, and volume of 1 is 4 by 3 pi r cube divided by the sides of the cube A. But here A is 2 root 2r. So if we put it, it becomes like this, and finally we get 74% of space is found to be occupied by the atoms, and free space is only 26%. So packing density is high in case of face centered atomic arrangement. In case of FCC, face centered cubic arrangement, we have the density of packing to be very high, which goes up to 74%. Now in case of BCC, body centered cubic, what happens? Let us see. One atom is at the center of the cell, which is in contact with two opposite corners. This is the corner, this is the corner, this is the center atom, which is in the center of the body. So this atom is in contact with this atom and this atom. So this is that atom, these are the two atoms, a body diagonal. So if this is A, this body diagonal will, the face diagonal will be root 2A. So this is root 2A, this is A, then this is the body diagonal. So root 2A is the diagonal of the lower face. Body diagonal will be R plus 2R. This will be 4R. So 4R square will be equal to root 2A. This will be root 2A whole square, and this is A, its square. So because it becomes a right angle triangle, so it becomes 3A square. So A becomes 4R by root 3. This becomes the value of A in case of BCC. Now we can find out the packing fraction. In case of BCC, the Z is 2. Value of Z is equal to 2 because corners 1 and body in the center of the body 1. So Z is 2. This is the volume of each atom divided by the sides of the cube. which is having 4r by root 3. If we calculate in this manner, divide, we get the packing fraction to be 68% with 3 space 32%. So this is not a very close packing as we find in case of FCC, where the packing fraction is 74%. Now, how to calculate the formula of the unit cell? We can find out the formula on the basis of this packing fraction, how the atoms are being packed. Contribution of the corner, for example, is 1 unit. Let us say the corners are being occupied by A atom. So let B be at the body center. Its contribution is atom. So phase contribution will be 3 atoms. Let the phase contribution, phase atom will be C, body center be B. So edges are 12 in number, and each edge is shared by 4 atoms. So contribution of the edge will be 3 atoms, because each corner is being shared by 4 unit cells. So contribution of each edge is 1 by 4. There are 12 edges, so contribution will be 3 atoms. If edge is having D, face is having C, body center is having B, and primitive is having A, then the formula for this unit cell of atoms occupying the body center, face center, edges and primitive corners will be A, B, C3, D3. B is body center, there is only 1 atom, so B 1 atom, A 1 atom. In case of corners, in case of face center, C, there are 3 atoms. If we take into account the total faces, if we take into account the edges, there are 3 atoms. So A, B, C3, D3 is the formula for the unit cell. So in this manner, the formula of the unit cells are being calculated. So I talked about how the packing fraction of unit cell is being found out by taking into account how many atoms are there in a unit cell, and which packing is the closed packing. As we see, in case of face center closed packing, 74% space is being occupied, so that is face center packing is the closest packing. And how in BCC, how in FCC, how in primitive cell, what is the contribution of each unit cell, that I discussed. And in my next class I will discuss about the 32 classes of symmetry. Thank you all for giving a patient hearing to my